How you doing? I'm Mr. Rose, and today we're going to be talking about the reasons why we learn math. In other words, we're going to be talking about some math that we're going to use in our life of physics. Specifically, we're going to be talking about some calculus. Because to this point, we've all taken a lot of math classes. But why have you taken math? What is the purpose of all of this math? A math class, at least in my opinion, gives you a bunch of tools to use, but never actually teaches you how to use them. It's like going to Home Depot, buying a chainsaw, but not knowing what to do. So we have this big toolbox full of things like chainsaws, and we have nothing to do with it. So we're going to start learning how and what to do with it, specifically talking about antiderivatives and derivatives. So starting with the basic, a derivative. What exactly is a derivative? A derivative is something that quantifies an instantaneous rate of change. Notice I didn't put any qualifier with it. I didn't talk about velocity, speed, acceleration, forces. I didn't talk anything about that. A derivative is something very simply that talks about an instantaneous rate of change. So where are we starting in physics? In physics, we start with speed, velocity, and displacement. So, for example, if you have a car, it's a very well-driven car. I know we all would like a car just like that. And with the car is driving, you can tell because I have this little arrow here and the little orange wind over there. And when you're driving your car, you glance down at the speedometer so you don't get pulled over by any police. And the speedometer, first of all, only gives you a speed. It doesn't give you a velocity because it's not actually giving you a direction. And the velocity, remember, is a vector quantity. So that speedometer is giving you the speed. What does that mean? The speedometer is actually giving you a definition. It is defining the rate at which your distance is changing, otherwise known as our speed. So we are going to kind of use speed and velocity a little bit interchangeably, which I know isn't the best thing. What do we know? We know based on these definitions. We know, for example, a velocity, using our just speedometer definition, a velocity is how much distance is changing per unit time. An average velocity, a change in position divided by a change in time, or a change in displacement divided by a change in time, that's very elementary. We are looking for instantaneous rates of change. So we're going to change this delta x to this dx dt. Now this is a calculus notation. This is just saying a very, very small change in position during that very small change in time, almost an infinitesimally small amount of time, an infinitesimally small change in distance. We can do the same thing with with acceleration. We can say acceleration is a change in velocity per unit time, which we know is an average acceleration. Well, we're going to make it a little bit more advanced. We change those deltas to d's, and we have a very infinitesimally small change in velocity per very small change in time. Now, how is this calculus? Well, this is essentially a derivative, and all a derivative is doing is taking the slope of a line. So here I've got some graphs already made up for us. I have a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. And it doesn't matter which section we're going to focus on. Let's focus on this middle section. If I want to take the slope of this line, remember slope is just rise over run, so I would have meters divided by seconds. And wait, meters divided by seconds, that is a meter per second, a change in position per unit time. So right here we can see that slope is really just our definition of velocity. Well, if we take the slope, notice it's a very constant slope. I drew this very deliberately, where it's kind of zero. Here is a changing slope, an exponential, and we're going to see that in a little while. Here I'm just looking at this constant. A constant slope gets me a constant velocity. I take the slope of this line, that value would be my velocity in the same amount of time. So I can transcribe that on a velocity versus time graph, just taking the slope, whatever value this is. It could be, say, 10 meters per second. This is 10 meters per second all the time. That's my velocity. Now here in this section here, this is a little bit of a change. That actually would be an exponential, and I know that just because of what it looks like. If I took an infinite amount of slopes. Taking, say, the limit. As my limit is approaching that exact spot, I would get an increasing number every time. If I plotted that down on a velocity time graph, I would get this nice changing velocity, starting at, say, 0 meters per second, ending at maybe 20 meters per second. That shows an acceleration. So this change in velocity is the same thing. It shows getting faster and faster just by taking a lot of slopes. That's what calculus is. It's taking a lot of data and putting it here. I can do the exact same thing. I know this is a constant slope. Well, if I took the slope of this line, meters per second, divided by seconds, change in y over change in x, I'd get some constant value. Let's go down to my acceleration. The slope of this line would be constant, a constant acceleration. Here, even though there's this big positive value, we know our velocity is never changing. The slope of this flat line is 0. Let's look at my acceleration graph. The slope transcribes to be 0. The car or the object is not accelerating at that point. These are taking derivatives over and over again. But what about an antiderivative? An antiderivative we often call integration. Well, if we can take derivatives, we can also undo our derivatives. So an antiderivative is undoing that derivative, basically starting with information here and getting all the way back up here. So what we're going to do is we're going to derive two of our motion equations that you should have already seen from the text. Starting with our very simple definition of what we already know acceleration is. Acceleration is our change in velocity per unit time. So I have that written right here. Acceleration equals dv dt. Now I want to be very clear. This is not a fraction. This is a calculus terminology. However, for reasons that you'll learn in calculus, remember, adding to that toolbox, we can treat it almost as a fraction. So what I'm going to do is I'm going to separate it out. I'm going to say, take that dt, put it over here. I'm going to say acceleration times my dt, my very small change in time, is a very small change in velocity. Now what we're going to do is we're going to take an antiderivative, and that's this big symbol here. So I'm going to take an antiderivative. Anything I do to one side, I have to do the other side of a times dt is equal to the antiderivative of dv. Now, this antiderivative is only looking at things that are changing. A is constant, so A isn't changing. If A was changing, we'd have a changing acceleration. That's something else. That's something called a jerk. So next time somebody calls you a jerk, say, hey, I'm not increasing my acceleration. I don't think I'm a jerk. And then you might get hit because that's kind of a jerk thing to say. But moving on, if acceleration is constant, what we do is we pull that right out of our integration. And now I have A times the antiderivative of dt. Now I need limits. Where am I looking? I have this very specific graph. I'm looking between two specific times. So from some initial time, say time equals 0, to some final time, t later. We're doing the exact same thing here, taking the antiderivative of dv from my initial velocity v naught to my final velocity v. Now notice I have a v naught here, not a 0, because I can't guarantee my velocity was starting at 0. Well, an antiderivative is undoing the derivative. So remember, to take a derivative, if I look at this t, take the derivative of t, that's really t to the first power. We take that 1, put it down there, and then subtract our exponent. 1 minus 1 is 0. T to the 0 is 0. So this is really just the antiderivative of 1 times dt. How do I get that? The antiderivative of dt, I'm going to add my exponent. 0 plus 1 is 1. A t to the first, and there's a divided by factor that we're going to talk about momentarily. So here I have at, and I'm looking at it between two different points. My limits of integration from time is starting at 0, ending at t. Do the exact same thing to the other side. My antiderivative of dv is just v, and again I can check that with a simple derivative, and I'm going from v naught to v. My next step, I'm almost done here, is when we evaluate. We always evaluate the limits of integration from the top to the bottom, or the final spot minus the initial spot. And I've done some simple math in my head here. I know a times t, I'm going to sub that t in there. So a times t is just at, and then subbing in my bottom value, 0 for t, this would be a times 0 is 0. So I would have at minus 0, which goes away. So my left side is just a times t. The right side of my equation, the same thing. We're going to do our limits of integration from the top minus the bottom, or the final minus the initial. I have v minus v naught. Those are my limits of integration. Now I take this last step, and I rearrange it to something that you should have seen. V equals v naught plus at. That is one of our kinematic equations. Now how is that taking the area under the curve? Well, let me show you how that's taking the area under the curve. If I start with this acceleration graph, and it doesn't matter what part I take, I'm arbitrarily going to look at this. If I ask a very simple question, how do you find the area of that? Well, we can see that this is a very complicated rectangle. Well, how do I take the area of a rectangle? Base times height. My base is a unit of seconds. My height is meters per second. When I multiply a meter per second squared times a second, I end up with meters per second. So the area of that curve, of that graph, that little section, is just something that is a value of meters per second. Wait a second. Meters per second is a velocity, which means this velocity must be the value of how fast I'm going. That is taking an antiderivative, going from acceleration to velocity. Now we're going to do the same thing. I want you to ignore this. We're starting up here. We're going to do the same thing looking at my, taking this equation and looking at it to get to my displacement equation. So first thing I did is I took the same exact thing. I know, remember, that V equals V naught plus AT, and I know that V is really just a change in position per unit time, or calculus work, dx dt. So I sub that in here. Dx dt is equal to V naught plus AT, and now I go through all the same steps. First thing I do, again, even though it's not a fraction, I can treat it very similar to, I distribute my dt to both sides, so I have dx equals V naught AT plus dt. Next thing I did was add my integrand, or my integration symbol. So this is actually something that's called an integrand. I have my antiderivative of dx from my two spots, my initial position to my final position. My initial position to my final position is equal to, I'm going to integrate this whole thing. The antiderivative, since time is changing here, I'm going from 0, some initial time, to a final time t. So now what I'm going to do here, the left side is very easy. It's exactly what we did before. The left side that I have written in blue, the antiderivative of dx is just x from some initial spot to my final spot. So I'm going to evaluate from x minus x naught. I can look down here, and this left side of the equation comes out to x minus x naught after I take my integration. The right side's a little bit more complicated. The right side of the equation here, we are going to distribute two things at the same time. It gets a little messy here, so I apologize. I'm going to distribute my integration symbol through, and I'm going to distribute my dt through. So that comes out to the antiderivative from 0 to t of v naught times dt that I have there, plus the antiderivative from 0 to t of a times t times dt. So now I'm going to take my antiderivative of both sections, and it actually is very, very simple. Look down here. This first part is very simple. The antiderivative v naught times dt, exactly what we had here, where v naught was is a constant, so that comes out, we just kind of ignore that. It's just like being a number. So this constant v naught times what's changing, my dt. Well, dt is changing from 0 to t, and we just saw going from 0 to t just gets me a t, because it would be t minus 0. So I have this part of my integrand evaluates to v naught times t, plus a, that's a constant that comes out of the integration symbol, from 0 to t of t times dt. Now this one's a little bit more confusing. It does get much easier. Here's a little sidebar, for example. We should know that if I took the derivative of d divided by dt with respect to t squared, how do I take a derivative? This is the shortcut. This is not the definition of the derivative. This 2 comes down in front of the t, so my exponent comes down 2t, and then we subtract, it would be whatever the exponent is, minus 1. So this is 2 minus 1, which is really just t to the first power. So the derivative is 2t. Taking a derivative, it's kind of like when you learn squares and square roots. I know, for example, if I have 25, the square root of 25 is 5. We're undoing the square. So I'm doing the same thing here. If I want to take the antiderivative of 2t, how would I get to t squared? Well, I'm undoing that derivative. So instead of subtracting, I have my exponent plus 1. So that would be 2. That would be 1 plus 1 is 2. Makes me the t squared. But what about that 2? Then we need to divide by the exponent, because 2t squared divided by 2 simplifies to t squared. So that's what we're doing here. We're going to take the antiderivative of t dt. In other words, what derivative did I need to take to get to that t? I needed to take the derivative of t squared divided by 2. If I look at that and I took the derivative, 2t, 2 minus 1, the 2's cancel, I get t. So the antiderivative, and this is a little bit confusing, we'll get better and better and more practice at it. The antiderivative of a times t dt is just a times t squared divided by 2. Now let's rearrange to something we've seen before. X minus x naught equals v naught times t, a over 2, plus 1/2 at squared. That is one of my kinematic equations. Again, what is that telling us? Let's look at this example right here. We see this is an at squared, so that gives us, we know some exponential function. That could be speeding up or slowing down. What it also tells us is I started this position. I had my velocity to get position. If I took, again, the area of any arbitrary point, we're just looking at the simple points right now. So if I took the area of this section, well, again, that is a nice, simple rectangle. The area is base times height. I can look at either the triangles too, 1/2 base times height. But I have meters per second times seconds. Well, meters per second times second is just a meter. So the area under this car is how far did I go? This would correspond with exactly how far I went in that given time. Started there and in there, subtract, I know how far I went. So that's a simple introduction to some calculus, something we're going to use throughout this course. There is a YouTube channel. I hope you can find it. Please, if you do, remember to like, click, and subscribe. Again, I'm Mr. Rose, and that's all I have for you today. Until next time.